As aldehydes and ketones contain the same carbonyl group, their properties and methods of preparation are quite similar. Methods for the preparation of aldehydes and ketones include oxidation of alcohols, dehydrogenation of alcohols, ozonolysis of alkenes, hydration of alkynes, reduction of acid chlorides, and reduction of nitriles. Let us learn about each one of these in detail. Let us begin our discussion with the preparation of carbonyl compounds from alcohols. You have already learned that primary and secondary alcohols yield aldehydes and ketones on oxidation. The process of oxidation of alcohols involves the loss of alpha hydrogen. That is, the hydrogen atom attached to the carbon bearing the OH group. In the presence of reagents such as pyridium chlorochromate, PCC, or acidified potassium dichromate, or acidified potassium permanganate. Now, since primary alcohols contain two alpha hydrogens, they can either lose one of them to form an aldehyde selectively in the presence of pyridium chlorochromate, PCC, or can lose both of them to form a carboxylic acid in the presence of acidified potassium permanganate. The conversion of a primary alcohol into an aldehyde is difficult because aldehydes are susceptible to further oxidation. One of the best reagents for the conversion of primary alcohols into aldehydes is PCC. Note that the oxidation of primary alcohol to carboxylic acids is usually accomplished by the use of acidified potassium permanganate. For example, ethanol on oxidation with PCC gives ethanal, but gives ethanoic acid in the presence of acidified potassium permanganate. On the other hand, a secondary alcohol loses its only one alpha hydrogen to form a ketone in the presence of acidified potassium dichromate. For example, isopropyl alcohol on oxidation in the presence of acidified potassium dichromate gives propanone or acetone. Another method of preparing carbonyl compounds from alcohols is by the dehydrogenation of alcohols. This method is suitable for the oxidation of volatile alcohols. It involves passing vapors of an alcohol over metal catalysts like silver or copper. Dehydrogenation of primary alcohols yields aldehydes, while that of secondary alcohols yields ketones. For example, when vapors of ethyl alcohol are passed over heated copper at 573 Kelvin, dehydrogenation takes place and ethanal is formed. However, isopropyl alcohol yields acetone on dehydrogenation. Carbonyl compounds can also be prepared from the ozonolysis of alkenes. Ozonolysis involves the cleavage of the double bond by the addition of ozone to give a cyclic product called ozonide, followed by hydrolysis in the presence of zinc dust. Depending upon the substitution pattern of alkenes, ozonolysis yields either aldehydes or ketones or both. For example, 2-butene yields 2 molecules of acetaldehyde on ozonolysis, while 2,3-dimethyl-but-2-ene yields 2 molecules of acetone. A molecule such as 2-methyl-2-butene yields a mixture of acetaldehyde and acetone on ozonolysis. Hydration of alkynes is yet another method for the preparation of carbonyl compounds. This method involves the addition of water to alkynes in the presence of mercuric sulfate and sulfuric acid to form aldehydes or ketones as the final product. For example, acetylene on hydration gives unstable vinyl alcohol, which tautomerizes to form the acetaldehyde. All other alkynes yield ketones in similar manner. For example, propyne gives acetone on hydration. Carbonyl compounds can also be prepared by the reduction of acid chlorides. Aldehydes can be prepared by the reduction of acid chlorides with hydrogen in the presence of palladium on barium sulfate in quinoline. This reaction is called Rosenmund's reduction. Aliphatic and aromatic aldehydes can be prepared by this method. Note that ketones cannot be prepared by this method. For example, adding hydrogen to acetyl chloride in the presence of palladium on barium sulfate in quinoline yields acetaldehyde. Similarly, Rosenmund's reduction of benzoyl chloride gives benzaldehyde. Ketones, on the other hand, are prepared by the treatment of acid chlorides with dialkyl cadmium. Dialkyl cadmium can be prepared by the reaction of cadmium chloride with Grignard reagents. For example, the reaction of methyl magnesium bromide with cadmium chloride gives dimethyl cadmium. The treatment of dimethyl cadmium with propanoyl chloride gives ethyl methyl ketone. Aldehydes and ketones can both be prepared from nitriles. Let's see how. Aldehydes can be prepared by the reduction of nitriles to imines followed by hydrolysis. The reduction of a nitrile to the corresponding imine by stannous chloride in the presence of hydrochloric acid, followed by hydrolysis to yield the corresponding aldehyde, is known as the Stephan reaction. For example, ethane nitrile on reduction in the presence of SnCl2 and HCl gives ethynylamine. This on hydrolysis in the presence of an acid gives ethanal as the final product. Alternatively, selective reduction by diisobutyl aluminium hydride DIBALH to imines followed by hydrolysis also yield aldehydes. For example, ethane nitrile on reduction in the presence of DIBALH followed by hydrolysis yields ethanal. Similarly, DIBALH can also be used to reduce esters to aldehydes, as shown here. Ketones, on the other hand, can be prepared by treating a nitrile with the Grignard reagent followed by hydrolysis. For example, propiophenone can be prepared by treating propane nitrile with phenyl magnesium bromide in ether followed by hydrolysis. Let us now look at the preparation of aromatic aldehydes and ketones. Aromatic aldehydes can be prepared from benzene or aromatic acid chlorides or methylbenzene or from benzyl halides. Let us discuss each method. Aromatic aldehydes can be prepared by treating benzene or its derivatives with carbon monoxide and dihydrogen chloride gas in the presence of anhydrous aluminium chloride or cuprous chloride. This reaction is known as the Gattermann-Koch reaction. For example, benzaldehyde can be prepared by treating benzene with a mixture of carbon monoxide and dry HCl gas in the presence of anhydrous AlCl3. As you have seen earlier, Rosenmund's reduction of benzoyl chloride with hydrogen in the presence of palladium on barium sulfate in quinoline also gives benzaldehyde. Benzaldehyde or substituted benzaldehyde can also be prepared by the oxidation of methyl benzene with chromyl chloride to a chromium complex followed by hydrolysis. This reaction is known as the Aldehyded reaction. Benzaldehyde can also be made from toluene. When toluene or substituted toluene is treated with chromic oxide in acetic anhydride, benzylidene diacetate is formed. This, on hydrolysis in the presence of an acid, yields the corresponding benzaldehyde. The hydrolysis of benzyl halides also yields aromatic aldehydes. For example, the hydrolysis of benzyl chloride, which is obtained by the side chain halogenation of toluene, gives benzaldehyde. Remember that this is the commercial method for manufacturing benzaldehyde. Aromatic ketones are more conveniently prepared by the Friedel-Crafts acylation. Benzene reacts with acid chloride in the presence of anhydrous aluminium chloride to give the corresponding ketone. This reaction is known as the Friedel-Crafts acylation. For example, benzene reacts with acetyl chloride and benzoyl chloride in the presence of anhydrous aluminium chloride to give acetophenone and benzophenone respectively. The physical and chemical properties of aldehydes and ketones are determined by the structure of the carbonyl group. It is, therefore, very important to understand its structure. Like the carbon-carbon double bond in alkenes, the carbon-oxygen double bond of the carbonyl group is composed of one sigma bond and one pi bond. The carbon atom in the carbonyl group undergoes sp2 hybridization in its excited state, leaving 1 out of 3 p orbitals unhybridized. The carbon to oxygen sigma bond is produced by the overlap of one sp2 orbital of carbon with a p orbital of oxygen. On the other hand, the carbon to oxygen pi bond is formed by the sideways overlap of the p orbitals of carbon and oxygen. The remaining 2 sp2 orbitals of carbon form 2 sigma bonds with the s orbital of hydrogen, as in formaldehyde, or 1 sigma bond with the s orbital of hydrogen and another sigma bond with an sp3 orbital of the carbon of the alkyl group. Like in other aldehydes, or 2 sigma bonds with 2 sp3 orbitals of the carbon of the alkyl group, as in ketones. Thus, the carbonyl carbon and the 3 atoms attached to it lie in the same plane with a trigonal coplanar structure and a bond angle of 120 degrees. While the pi electron cloud lies perpendicular above and below the plane. It is important to note that the carbon-oxygen double bond in the carbonyl group is different from the carbon-carbon double bond in alkenes. In case of alkenes, the pi electron cloud is equally shared by 2 atoms, whereas in the carbonyl group, the pi electron cloud is attracted more towards the oxygen atom due to its greater electronegativity. Consequently, in the carbonyl group, the oxygen atom acquires a partial negative charge, while the carbon atom acquires a partial positive charge, thus making the carbonyl a polar group with a dipole moment value of 2.3 to 2.8 dBi units. However, the high value of the dipole moment can be accounted for both the inductive effect and the resonance effect. Now, let us look at the physical properties of carbonyl compounds. At room temperature, formaldehyde is a gas and acetaldehyde is a volatile liquid. Other aldehydes and ketones are liquids or solids at room temperature. Aldehydes and ketones have higher boiling points than hydrocarbons and ethers of comparable molecular weights. This is due to the weak intermolecular dipole-dipole interactions. Observe this table about compounds of almost similar molecular weights, 72 to 74. We see that non-polar hydrocarbons like N-pentane and weakly polar diethyl ether have lower boiling points than that of polar N-butyraldehyde and ethyl methyl ketone. However, their boiling points are lower than that of N-butyl alcohol and propionic acid. This is because carbonyl compounds are not capable of forming intermolecular hydrogen bonding by themselves, since they contain a hydrogen bonded to carbon, but not to oxygen. Aldehydes and ketones are soluble in the usual organic solvents like benzene, ether, and chloroform. To know their solubility in water, refer to this table, which shows the solubility of a compound in grams per 100 grams of water. We see that the lower aldehydes and ketones, such as formaldehyde, acetaldehyde, and acetone, because of their ability to form hydrogen bonding with water, are miscible in water in all proportions. Notice that solubility decreases with an increase in the length of the carbon chain. The lower aldehydes and ketones have a characteristic pungent odor. With an increase in the size of the molecule, the odor becomes less pungent and more fragrant. Therefore, many naturally occurring aldehydes, such as vanillin from vanilla beans and cinnamaldehyde from cinnamon, and ketones such as acetophenone, are used to blend perfumes and as a flavoring agent.